So James, definitely thank you for being here today. I'm very excited to have you. I know you have something prepared for us, so I'm really curious. What are you currently, intensely thinking about right now? Like, what's sort of on your mind about physics?
So I guess the crux of what I'm interested in is the difference between two kinds of randomness. I sort of sub-vocalize it to myself as a tale of two randomnesses. So when I was an undergraduate and I learned about statistical mechanics, and even younger than that in high school when you learn about probability theory, you're sort of made to understand that probability theory is making up for a kind of ignorance that you have about the systems that you're studying. So for example, if I flip a coin, I can describe the outcome of 100 coin tosses in terms of the number of times in many, many trials of that experiment that I would get 50 heads and 50 tails, 60 heads and 40 tails, and so on and so forth. And I'm meant to understand that we describe the system in this way because the initial conditions that predestine the coin at the moment it's flipped to end up as heads or tails are just too complicated for us to know. There are all kinds of interesting philosophical questions that have to do with the interpretation of probability, which I find fascinating, but I'm certainly not equipped to answer those, and I would encourage viewers to look into them. But what I'm interested about is a new kind of randomness, a different kind of randomness from that kind of randomness. And it's a randomness which is sometimes distinguished from classical randomness using this word ontic. Okay? So in philosophy, we talk about epistemic and ontic. Epistemic is about the state of our knowledge of how things are, and ontic is in some sense about how things actually are. Okay. And the kind of randomness that comes in a coin toss is what we might call epistemic randomness. It's not that the coin toss is fundamentally a stochastic process in terms of the classical equations of motion that govern the path of the coin. It's that we are ignorant of those initial conditions, and so we, through some process, are able to model our ignorance using classical probability theory.
I see, okay.
When you learn about quantum mechanics, what you discover is that there are two fundamental facts about quantum systems that make them undescribable in terms of this classical framework. In some sense, the kind of randomness that exists in quantum mechanics is not simply randomness induced by an ignorance that we have about the state of the system, which in principle could otherwise be known. It is an ignorance which to many people seems to be fundamental to the universe. And in this sense, we call it ontic randomness that has to do with the actual state of affairs in the universe itself. Many interpretational questions abound from this. No one has yet, I think from a philosophical perspective, given a kind of complete and uncontroversial explanation of this. But
So just to clarify, but this randomness, this quantum randomness, it's fundamentally different from the classical or sort of the probability theory that you might be taught in your undergraduate degree type of randomness, right?
That's exactly right. So there are actually theorems, two theorems in particular. One of them is Bell's theorem, and the other is the Kochen-Specker theorem. I hope I'm pronouncing that correctly. And these two theorems are basically no-go theorems. They basically explain that the outcomes of quantum mechanical measurements just cannot be described by classical probability distributions. There's just no way.
Okay.
And so this difference in two kinds of randomness manifests as a difference in two kinds of probability theories. So first of all, let me maybe specify what these two principles are. The first principle, best illustrated perhaps by the double slit experiment, is the principle of superposition. So fundamentally, we understand quantum phenomena to be described by waves, by wave functions. And waves can superimpose onto one another. And this means that when I describe the joint probability distribution of two separate systems, the vector or the wave that describes that joint system might be such that it cannot be factored into a wave on system A product or a product of wave on system B. So it might be that the description of a system is fundamentally collective in this sense. You can't simply model the statistics of the whole system by analyzing the statistics of individual systems.
I see.
It's a sort of principle of superposition. And the other principle fundamental to quantum mechanics is the Heisenberg uncertainty principle. So the idea that when I measure a particular observable, if I get an outcome for that measurement, it induces a fundamental and irrevocable uncertainty in other complementary measurements. So a standard example is the position and the momentum of a quantum particle. If I measure the position of a particle to infinite precision, then I lose any knowledge whatsoever of its momentum, and vice versa.
Yep.
And so these are the two principles that are conspiring to make quantum physics fundamentally different from classical physics. So why is that interesting? What is it about this that I find so fascinating? In my field of physics, we're interested, as are you, in the physics of many bodies. So in particular, in my case, the physics of materials. How do materials organize themselves? What kinds of behaviors do materials exhibit when they are put into magnetic fields or currents or beams of neutrons and so on and so forth? And what we can understand is that the outcomes of experiments on a material can be divided into two kinds of categories based on the two kinds of randomness that are operating. Okay. So there is classical randomness involved and the outcome of measurements on materials, but there is also quantum randomness involved. And the interest of my research is to try to understand how that quantum part of the randomness can be used to identify the patterns of organization and excitation inside of the material. Okay. So this is, in broad strokes, what I'm very interested in right now, and what I sort of want to discuss with everyone through the course of this video. And I maybe want to start out by putting up some goalposts that might be more familiar to people than some of the discourse that I've just offered. And I want to talk about entanglement. Okay, so this term entanglement. So I mentioned before that the superposition of waves is the thing that introduces entanglement into a physical system. But let me introduce quantum correlations in the following way. Let's imagine we have our electron again. And now I'm going to introduce the following state. Just one electron, not two, just one. We're not even talking about entanglement here.
Sure.
Just getting a feel for quantum correlations. So there's a state, and I can make the density matrix of this state quite easily. That's the density matrix corresponding to that state. And I'm going to make another, so I'm going to call this one Q. I'm going to call this one T. Here, I'm going to give you another state, and I'm going to give you a puzzle. Okay. So now I'm going to describe an experiment to you. I'm going to give you one of these two states. Okay. So I'm either going to give you an electron that is always in a superposition of its up-down state. That's experiment one. Okay.
Yeah.
Or I'm going to give you heads or tails, an electron which is just up or just down, with probability 50-50.
Sure.
Can you tell the difference between these two scenarios? What is the difference between these two scenarios? And naively, we might say to ourselves, well, there's no difference. You know, in scenario A, I make a measurement on my electron. I have a Stern-Gerlach device, for example. I make a measurement on my electron. And 50% of the time, the electron goes up. And 50% of the time, it goes down. All right, so I've got these two measurements, 50-50. And the same is true of experiment B. You know, 50% of the time, it's going to go up. And 50% of the time, it's going to go down.
Sure.
So what's the difference? How do I tell the difference? Well, the trick is to measure this state, but in a different basis. This is the trick that quantum mechanics allows us to do. So if I take this state, my quantum state, and I imagine not measuring it along the z-axis, but measuring it instead along a rotated axis, say the axis left-right, instead of, so we're in the basis up here, we're in the basis up-down. And here I'm talking about the basis left-right. So I'm measuring in the sigma x basis.
Sure.
What you'll find is that this state, which previously was giving you 50% up, 50% down, is now going to give you strictly left in its measurements 100% of the time.
Okay.
But this state which I've labeled thermal T, is still going to give you 50% up and 50% down.
I see. Okay.
So in some sense, understanding the way in which our state responds to different measurements is the essence of understanding the difference between quantum fluctuations, quantum randomness, case A, and incoherent thermal randomness, case B.
Sure.
This is a sort of blueprint of what we mean when we talk about quantum and classical randomness. Okay, so So we can see here that I've constructed the state via some kind of superposition. That's the way that I arrived at the state. So now let's start to try to approach this many-body case that we're so interested in. And let's examine instead the following state, the so-called Bell state, sometimes we'll call it. That's the whole basis of Bell states that you can construct out of two spin electrons, a four-state basis of Bell states. But never mind, not important. This is one particular Bell state, the singlet state. This is sometimes called in condensed matter because it's a state with zero total angular momentum. And in many body form, the state forms the ground state of interesting spin models, such as the spin one Heisenberg model. Okay, so now I want to explain a bit more about what I mean about not being able to decompose this state because of the principle of superposition into a state on just A and B. What I mean by that mathematically is that I cannot find an A and I cannot find a B such that this is true. There's no way for me to make this equal this, where A is defined purely on subsystem A and B defined purely on subsystem B. This state is, therefore, we would say entangled.
Okay.
Now, there's a sort of standard theoretical trick for noticing that a state is entangled, and it involves looking at the Shannon information of the state. So I want to start to introduce this idea of information theory as a probe of quantum versus classical correlations. So in classical information theory, if I have a probability distribution described by probabilities P sub j, the Shannon information of that distribution is going to be sum over P sub j ln Pj. This quantity here, this logarithm of P sub j, you can kind of think of as the information that would be contained in an event with probability P sub j. So for example, the sun rises every day. You know, every day I've been alive, the sun has risen. So my entropic prior for the sun to rise is like, it's going to rise 100%. And so when it rises tomorrow, I learn nothing about that fact. But conversely, if the sun didn't rise tomorrow, that would be the most stupendous occurrence, and it would completely change my worldview. And so the lower the probability of the event happening, the more information it contains when it does happen. That's the sort of principle that Claude Shannon is thinking about when he wrote down this expression, along with a couple of other considerations about the properties that information should have. You know, information should add in certain ways that make sense mathematically. I won't get into those details here, they're a bit technical. But this is the form that we arrived at, the natural logarithm of the probability, or the logarithm base 2 of the probability. So units of bits tends to be the way we talk about this. Perhaps actually it's more correct for me. I shouldn't write this as log. I should write this as log base 2. Okay, so we can ask ourselves, what is the Shannon information in the probability distribution contained in a quantum state? And this guy, von Neumann, pretty smart dude, probably many of your viewers have heard of von Neumann, generalized Shannon's notion to the case of quantum states. And what von Neumann said quite simply was that the von Neumann entropy of a state represented by a density matrix rho. So we're imagining now that I've taken my pure state and I've turned it into a density matrix rho, is going to be equal to the trace of the log base 2 of the density matrix. So that's my Shannon, that's my von Neumann entropy, my quantum Shannon information.
Sure.
Now, one thing I'll notice about this definition is that if I have any pure state at all, I can always represent the pure state having rank 1 as a density matrix.
Yes.
Right. So in the basis of the state itself, you know, this is just 1. It's likelihood 1 that this will happen. And no matter what my density matrix is, I can always diagonalize it. So I can always express the density matrix as a sum over J of probabilities and eigenstates of the density matrix, which I'll denote J.
Yes.
And for pure states, I'll always find that P sub J is equal to 1 for the pure state. And 0 elsewhere. So what that means is that if I compute the von Neumann entropy for a pure state, I get 0. For a pure state. But if I compute the von Neumann entropy for a mixed state, I'll get some non-zero value, which sort of recovers. As a matter of fact, the Gibbs entropy, which we learned about in statistical mechanics, is nothing more than a special case of Shannon information. And so in finite temperature systems that are in a mixture, a thermal mixture, I just recover the Gibbs entropy. And so that's a very satisfying result. But if I take my state psi, if I take my density matrix corresponding to psi, and I imagine tracing out one of my two subsystems, so I say this is the density matrix just on subsystem B, and I've traced out subsystem A here. That's what I meant to like this. And I now look at the von Neumann entropy of this state. I can make the following observation. Okay. If the state initially was separable, so if the state was not entangled initially,
yep.
If I write the state as, for example, AB, and I trace out subsystem B, then what will be left over is still a pure state. It's as pure as the original state was. And so this will be 0 if the state is separable. And it will be non-zero if the state is entangled.
Okay.
Most of the time when we talk about entanglement in the literature, this is what we're talking about. We're talking about this
yep.
phenomenon of von Neumann entropy being non-zero on the subsystems.
Yes.
And what I want to do here is explain how this is actually a very special case of entanglement of quantum correlation. It does not, for example, account for the first example I showed you, right? That's an example where quantum correlations, quantum fluctuations are present in the system. But this probe of quantum correlations wouldn't tell you that. You know, from the point of view of this probe, a state in superposition, a state not in superposition in any given basis is equivalent as long as it's pure. Its von Neumann entropy will be 0.
Yes.
And so what I want to do is talk about how by interpreting the space of quantum states geometrically, we can capture a whole range of quantum phenomena and quantum correlations that we would normally not consider if we were analyzing simply the von Neumann entropy. So let me maybe explain to you how that can be done. And to do that, I want to introduce the following idea. I want to take a step back and talk a bit more about classical probability theory, and an idea from classical probability theory that goes beyond Shannon information. And then I want to talk about how that generalization, the generalization of that concept, can help us answer our question about how do we measure quantum correlations. So for a given probability distribution, I've told you that we have this notion of a Shannon information. We can imagine that I have a whole space of probability distributions.
Sure.
And these probability distributions are maybe parameterized in some way by a parameter theta. So here's a state. And I can ask the question, if I do a certain number of measurements, if I do, say, m measurements, how easy is it for me to distinguish p of theta from p of theta plus d theta? What is the difference between these? I want to sort of write this minus sign, but I'm not just subtracting them. I'm asking how distinguishable are they? So a concrete
so theta here is some parameter that's parameterizing my space of probabilities.
Yeah. So let's do a simple example. Right? I've got a coin, and the probability of heads is theta, and the probability of tails is 1 minus theta.
Okay.
And we're gonna play a game. You're gonna flip the coin, and you're gonna flip it any number of times that you want, and you have to guess what the value of theta is. So the coin is not a fair coin, and you're going to do some number of flips, and you're going to try to guess what the value of theta is. And my goal is to make that as hard for you as possible. I want it to take you a really long time to make a good guess about what theta is. So we can imagine a couple of limiting cases, right? What if I chose theta equal to 1? That's a pretty bad move on my part, right? Because then the coin's always going to be heads. And by the time you flip this thing like 15, 16 times, you're going to start thinking to yourself, gee, like this coin is just never turning up tails. That's really, really extraordinary. Yeah. But by comparison, if I choose theta to be something like 0.4, that's going to be kind of tricky. You're going to have to, do a couple trials. You'll see, okay, I got 2 heads, I got 3 tails, I got 4 heads, I got 5 tails, something like this. It's going to take you a long time to hone in on the idea that theta is equal to 4. So in some sense, the ability of me to distinguish the distribution P of theta equal to 1 from its neighboring distributions is a lot easier than distinguishing P of theta equal to 0.4 from its neighboring distribution.
I see.
This state is more distinguishable from its neighbor's state. And the concept that quantifies this is called Fisher information. Classically.
Okay.
And we can think of Fisher information as sort of the shape of the Shannon information. Okay, so what do I mean by that? Well, in the Shannon information formula, I had this Pj times log root 2 of Pj.
Yep.
And this here, if I imagine that this is kind of my uncertainty in my system, the derivative of this guy with respect to my parameter theta, which in this case is called the derivative of this guy, okay, is called the score function. And its average is 0. So the expectation value of this is 0.
I see.
You can prove that straightforwardly. It's not too difficult to show that's true. So instead, what we look at is the variance of this quantity. We look at the fluctuations of this. So we look at the expectation value of the square of this quantity minus 0. So this is the definition of classical Fisher.
Yes.
Okay. So in the way that I've described, this defines a notion of distance. Two probability distributions are further apart if they're more easily distinguishable from each other. And two probability distributions are closer if they are indistinguishable from each other. Mm-hmm. And so the picture that we have here is a picture of a space of probability distributions with a metric, a measure of distance on the space. And you can actually show, for the math aficionados watching, that the Fisher information is the unique Riemannian metric for the space of classical probability distributions. So in other words, if I consider that space as a kind of Riemannian manifold, smooth manifold, then this is the unique way of assigning notions of distance to that manifold.
I see.
Okay, so that's quite interesting. So how does this get us leverage on our quantum problem? Well, we can take our notion of, start this here in a different sheet. We can take this notion of classical Fisher information, and we can extend it to what I'm going to call quantum Fisher information, QFI. And we can write down an expression for this. So we can say that the standard expression would be something like this. And I'll try to, this is maybe get a bit in the weeds mathematically. We don't necessarily need to run through the details of this, but it's nice.
No, I think it's fine. Just keep going. If there's like if this is necessary to understand it, then keep going.
So this operator here is the sort of generalization of the operator that of the expression we just spoke about. So the classical Fisher information has a form. If I write it out, that looks like this. So this is the likelihood of the outcome of an experiment being X. For example, the likelihood of the outcome being heads, given that I have set the likelihood of heads to be theta. So if theta is 0.4, what is the probability that heads comes out? Is basically what this is. And then here I have the derivative of that with respect to theta squared. And I integrate over the sample space. That's the classical version. So the quantum version is this trace. The trace sort of replaces the integral. And instead of, here's a trick, right? Now in quantum mechanics, I'm working with operators. The operators do not commute. And the fact that the operators do not commute is the reason why this quantity is different.
Okay.
That's the whole point, is that non-commutativity is what induces these extra quantum correlations. But how do I deal with the fact that I'm dividing by the density matrix? Do I divide on the left? Do I divide on the right? How do I handle that? One choice you can make, and it is an arbitrary choice, there's in fact no correct choice. One choice I can make is to handle it symmetrically. So I can imagine that the 1 over the density matrix, if I multiply on both sides, is sort of treated symmetrically. So this operator here corresponds to the derivative of the logarithm. And it's defined implicitly through this relationship. So you could sort of imagine that if rho was just a number, I could divide by both sides and get 1 over the density matrix rho is equal to the logarithm derivative of the density matrix. And so that kind of covers this classical picture that I've described here. Okay, so now we are equipped to start asking the question, how does the geometry of the space of quantum states differ from the geometry in the space of classical states? I can return, for example, to my quantum coin experiment where I just had a simple superposition. This. And in the zero temperature case, in the pure state case, the Fisher information is actually just the variance of an operator of a measurement with respect to the state side. So I can look at this state and I can ask, okay, well, what is the variance of measurements along different axes? So I'm going to parameterize the axis by theta and phi here for the state side as a function of theta and phi versus what is the variance for my thermal state of the same operator.
Sure.
And what I would find is that this variance here is always fixed. It's always fixed to be maximal because the state is always maximally mixed. But this state as a function of theta and phi is going to exhibit a behavior where it goes from 0 up to a maximum value and back down again if we take a slice, say, of theta.
Okay.
So you can see here in this cartoon that if I ask myself what is the Fisher information, in this case just the variance, of an operator, a magnetization operator parameterized by theta and phi, that as I vary theta and phi for the quantum case, for the pure state, I get this sort of shape that responds to that based on whether the operator commutes with the state or does not commute with the state. So the maximal Fisher information is coming when my qubit is aligned north-south and my measurement is aligned orthogonal to that. By comparison, for the thermal case, I just get a fixed variance. It doesn't matter. It doesn't matter what theta and phi I choose. And so we can see here how this notion of variance, which we're going to start interpreting as a kind of geometry, can tell us something very profound about the differences between classically correlated states and quantum mechanically correlated states. We had our state written down here, and we understood this idea that this is a two-partite state, a two-particle state. They cannot be written as a product state. And so it cannot be written as this. And so we understand that the state is entangled. And we further discussed how looking at the von Neumann entropy of the reduced density matrix for this state, being non-zero is an indicator of entanglement. That indicates that when I traced out one part of the system, I lost information I introduced from the perspective of that subsystem, incoherent fluctuations. And so the von Neumann entropy is now zero, where the von Neumann entropy of the whole state was zero. Okay, that's pretty straightforward. And we also demonstrated how, we can also demonstrate how the Fisher information achieves the same result, right? So if I imagine looking at the Fisher information for this state, and I imagine, for example, looking at the variance of an operator, let's pick an operator that we can use, the magnetization on state A minus the magnetization on state B.
Sure.
That's one operator that we might imagine using. We could also use the magnetization on state A plus the magnetization on state B. There are different choices that we can select here. And this is the point of the Fisher information, is that it doesn't just tell you that entanglement is present, but it tells you with respect to what observable entanglement is present. If there is a direction in my space of states where the state is unchanged by an evolution in that direction. So for example, if I've got a state and I ask myself, how much does the state change along a direction parameterized by the operator O, and the answer is it doesn't change, then what that tells me is that this state is not entangled with respect to measurements of O. Measurements of O are going to be purely classically randomized, if at all randomized. They might be deterministic if there is no temperature. But if by contrast I have another state, call it M, and the state changes a great deal with respect to measurements in terms of M, then this state must be very entangled if I'm at zero temperature with respect to this quantity. And so this is the idea that Fisher information, once I've picked a parameterization, I can tell how entangled I am along that parameterization. And so for this particular operator here, I can just look at the total magnetization. This is the easy choice to pick. And I can look at the Fisher information of SA plus SB, where S now is not the von Neumann entropy, but the magnetization on side A and the magnetization on side B. Maybe I want to look in just the Z direction. So not looking at the magnetization. It doesn't really make sense to ask what the magnetizational on all axes are. So I pick the magnetizational on the Z axis.
Sure.
And what I can find is that this is extremely entangled. In fact, this variance here is going to be equal to 2. And there's a theorem, a proven theorem, which shows that if the Fisher information per site is going to be equal to 2. So the Fisher information itself would be equal to 4. The Fisher information density is equal to 2. There's a theorem that says that if for an n-partite state, the Fisher information per site is greater than or equal to a number m, where m divides the system size, then my state is m plus 1 partite entangled.
Okay.
So in this case, I can see here that my, this is going to be equal to 1. So I can see here that my Fisher information is equal to 1, and 1 does indeed divide 2, and so my system is 2-partite entangled. So the Fisher information not only tells me that I am entangled, it not only tells me with respect to what operator I'm entangled, it tells me how entangled I am. So imagine now n is very big. Imagine now n is like 1 million. How do I bring these tools to bear in analyzing the quantum correlations? Well, the standard approach for a long time has been to divide the system into subsystems A and B, to trace out subsystem A, so to perform the same analysis as here, and to see how large the von Neumann entropy on a subsystem is. And the larger it is, the more entangled A and B are with one another. So this is a kind of bipartite entanglement. It's asking how entangled is subsystem A with subsystem B.
Sure.
But what the Fisher information is giving us in excess of this is, if I take a state of n particles psi, and I try to write it in some basis, okay, so I'm summing over J states here. So maybe I've managed to factor it into J state. Then what the Fisher information is telling me is the largest of these partitions, given that I factored my state as much as I possibly could factor it. And so if the largest of these partitions is 50 and my system size is 1,000, then my system would be 51 partite entangled, at least.
I see.
Telling me how many particles are participating in the most entangled partition of the state. And so it's giving me a much sort of finer, detailed resolution of the structure of the space of states. And so what I want to sort of propose is that this geometrical picture of quantum mechanics, understanding quantum mechanics in terms of the geometry of the state space under different parameterizations, gives a very rich picture of the difference between the quantum and the classical fluctuations in the system, which allows us to refine how entangled the system is, how much of a superposition it's in, with respect to what variables is the measurement outcome going to be entangled, and with respect to what variables will it not be. And all of this is operationally well-defined. It's all well-defined from an experimental point of view, because it's making reference to precisely how distinguishable different probability distributions are. Where by contrast, the von Neumann entropy is relying on specific knowledge of the density matrix itself. And so I want to propose that when we talk about entanglement, we're really only talking about part of the story. The bigger story is this story of quantum correlations, ontic randomness, and how does it show up in our systems? How can we tell that a given measurement outcome is ontic and not epistemically random? To what degree is the quantum fluctuation playing a role in that measurement outcome? So we've been talking a lot about this idea of entanglement and these ideas about quantum correlations. And so what I want to maybe mention now something a bit more specific to my work. So what I've explained so far is fairly standard in the literature, and I want to sort of offer a new direction that has been building momentum for the last few years, and I'm very excited about trying to understand more about it and try to contribute to it. And it's this idea that phases of matter, going back quite a long time, going back maybe 100 years, phases of matter could be understood in terms of local patterns of organization. And the fact that we now understand that states of matter at very low temperatures under the right circumstances can be predominantly governed by quantum fluctuations, we want to begin to probe what kinds of quantum fluctuations. If a system is ordered, but not ordered in a sort of local way, ordered instead in a kind of global way, how can we probe those global forms of organization? So there's a framework that we use to understand this, and the framework is the framework of topology. So a simple kind of example is that, a sphere is fundamentally a different kind of thing than a donut is.
Sure.
And in sort of like fashion, in kind of analogous fashion, in phases of matter, there are states of matter that locally look the same, right? So I can take two phases of matter and I can make a little measurement of one piece of the phase of matter, and they both look the same, right? If I zoomed in on this little piece of the sphere and this little piece of the torus, I might say to myself, hey, these are pretty similar. Like, I don't really know the difference between these two things. But in a global sense, they are completely different. And these define different kinds of, we call them topological order. And the trick in detecting them, the challenge in detecting them, is precisely this fact that local measurements can't distinguish between them. And you need something a bit more wily, if you will, to determine whether or not you're in a topologically ordered phase and what kind of topologically ordered phase you're in. And so I'm very interested in the way that this notion of topology links to this notion of geometry that we've been talking about, and how this notion of geometry might offer us some experimental avenues to determine the topology, topological order of a given phase of matter when local measurements would suffice. And so hopefully we can do a future video and maybe delve into this topic in a little bit